Today we're going to take a look at the Gnome sort challenge from Topcoder. Now Gnome sort is a sorting algorithm that is similar in aspect to insertion sort in that it deals with one item in the array at once, but then it works similarly to bubble sort when it starts moving those items to its preferred location or to its sorted location. It does this by swapping the item with the item preceding it as it moves that number or string to its appropriate location. Now, in this particular Gnome sort, we will discuss in a minute how I've optimized it in one way, rather than once it swaps the item to its sorted location, checking every single index it's been through before. It keeps track of the last indexed index and then moves the search to that point so that it can continue where it left off, because up to that point every number in the array should already be sorted as it goes through that loop. Now, one other thing about Gnome sort is that it does not require any nested loops to sort the algorithm or to sort the array. Rather, it only requires one loop to move items into its sorted order. Now, the way it does this is as I said, it takes in an array and then it indexes the first array, or the array at index 1, and then the array at index 2. Now, the reason why it takes that first index as index 1 rather than index 0 is because what it's going to be doing is once it takes or starts checking indices, it will check the index prior to the number that it's currently looking at. And if the number that it's currently looking at is less than the index preceding it, or I minus 1, it will then swap those places. Now, what it also does is if it finds that, and this way, the first check will always be with index 1 against index 0. So rather than checking to see if it's at the start of the array, it automatically jumps in at index 1 and then starts checking, or comparing, I should say, the numbers between 1 and 0. Okay. After that, it moves through the array, and as it moves through the array, if index minus 1 is less than or equal to the index that we approach the array at, what it's going to do is it's just going to move index to that next array. Now notice before we said the index started at 1 and the last index started at 2. So index becomes last index, and last index becomes last index plus 1. Okay, so we're slowly moving through the array by 1, and what we're doing with that last index is basically just keeping that location where we want to re-access the array after we start swapping any numbers that need to be swapped. Okay, now if the array index minus 1 is not less than the array, that's when the swaps are happening. So it swaps the previous index with the current index that we're accessing by just doing a simple parallel swap here. After it does that, it moves index back minus 1 because it's got to make sure that the number that's been swapped is where it's supposed to be. So again, once we start swapping numbers, we need to make sure that the swapped number is then in inserted order. And we'll see that once we actually display the algorithm working on an array. Once that occurs, then again, the index is set to last index, and last index is set to index minus 1 um, if it reaches the beginning of that array. So again, it's checking all those positions in the array prior to the indexed array and the swapped number. And once it reaches the beginning of the array, it says, hey, look, this number is absolutely in order. Let me go back to that last accessed point in the array. Now, once it reaches the end of the array, which is length of the array minus 1, what's going to happen then is it will return that new sorted array. Now, we'll notice that this runs in a while loop, and as I said, it runs until the index is equal to the array length. So once it reaches that end point and the while loop progresses one more, then the loop will stop, of course, and then it will return the sorted array. So let's go ahead and see that happening. Now, I'm going to go ahead and run the RSpec tests before we take a look at the array, and this is just to show you that everything's passed okay. So we're going to do the bundle exec RSpec, and again, if you follow the directions in the README file, we can go directly to the RSpec file by typing in spec / gnome sort spec.rb. You'll notice that all of the tests pass. There are 0 failures. And now let's see what exactly is happening once we test that array. So let's go ahead and clear the screen. And just as my previous sorting methods test, I'm going to pass in a shuffled array. And this array is going to be 10 numbers that are randomly chosen between -100 and +100. This way we can see how it deals with negative numbers. If 0 is in the array, it should deal with 0 appropriately, and of course any positive numbers should all be returned in sorted order. Then I print out the random array, and then as we are going through the algorithm, what I'm going to do is I'm going to print the array whenever there's a swap, so that we can actually see where those swaps are taking place. Now again, this is optimized, so once that swap is taken place all the way to the first index, if there have been no changes at that point, it's going to jump back to the last indexed point in the array and then continue sorting. So let's go ahead and see that in action. Let me make sure my file is saved. We will make this window just a little bit bigger so we can actually see what's going on. Clear our screen and run the code. Now this is again Ruby, and then we are in the RSpec file. The spec file, and the file name is gnome_sort.rb. Okay, so as we can see, we took in a random array of -88, -77, 10, 3, 47, 44, 59, -8, 43, and 13. So we can already tell we're going to have some swaps in here because this array is not in sorted order. So starting with -77, again, because we approach this index at index 1, so that we can start checking the previous index for sorted order. So again, we start at index 1. The last index is set to index 3, so that will be the new point we jump in if there are any swaps prior to 3. -88 is less than -77, so no swap there. Then -77 is less than 3, so no swap. 3 is less than 10, no swap. 10 is less than 47, no swap. 47 is not less than 44, so then we have our first swap. Now 10 is less than 44, so no swap. Again, the rest of these are sorted. Again, it's no swap because obviously 10 is less than 44. So then we move to the next line. Now remember, our last index point was 44, and that's where 47 is now. So we start at 47, and we go, is 47 less than 59? It is, so no swap. What about 59 less than 8? This is false, so these two are going to swap. Then it says, is -8 less than, or is 47 less than -8? And it's not, so it swaps again. Is 44 less than -8? No, so it swaps again. 10 less than -8? No. 3 less than -8? No. -77 less than -8? Yes. So then we go all the way back to 59 because that's where we started the swap. Then we ask, is 43 or 59 less than 43? No, so swap. 47 less than 43? No, swap. 44 less than 43? No, swap. 10 less than 43? Yes, so we stop and we move back. So we're moving back to where we were at 43. Then we say, is 59 less than 13? No, swap. 47 less than 13? No, swap. 44 less than 13? No, swap. 43 less than 13? No, swap. 10 less than 13? Yes. And at that point, we have reached the end of our array where 59 is now located. Remember, that's where 13 originated at, so that's our last indexed point. So we return back to there. There's nothing beyond that, so our array is at this point sorted. So it returns -88, -77, -8, 3, 10, 13, 43, 44, 47, and 59. So as you can see, it returns an array in order. You can clearly see when the swaps happen and then it jumping back to that last known point. So this way we get that optimized array. If we weren't holding that last known point, it would have to go back and check every one of those numbers again from the last swapped location. So if a number was at the middle of the array, swapped all the way back to the beginning, then it would have to check every number back until it reached the middle of the array, just to check to see if those numbers were swapped, if it wasn't holding on to that last accessed index. So again, this is Gnome sort. It is an optimized version of Gnome sort, again holding that last point that we access. If there are any questions, please feel free to put them in the forum and I will answer them as soon as possible. Thank you.